First of all, Jason Kalirai, who is the missionary executive for civil space at APL, and then he will pass the floor to our new sector head, Bobby Braun. So, thank you.
Okay, great. Thank you. Welcome, everyone. Thank you, Rachel. I think it's been a little more than 2 years since we hosted an LSIC conference here at APL, so I want to welcome everyone back to APL, and we can take advantage of this the wonderful new building we have here, Building 201, we call it. This is where a lot of the research that cuts across all of the Applied Physics Lab occurs in our Research and Exploratory Development Department. A wonderful facility, and looking forward to interacting with everyone over the next couple of days. We've got a couple hundred people here and many more online, and it's been remarkable to see the growth in the Lunar Surface Innovation Consortium. So Rachel asked me to speak a little bit about the broader work happening at the lab that supports NASA. LSII and LSIC are very important parts of our civil space program, but we also do a lot of work with NASA's Science Mission Directorate, and so I was happy to do that, provide a little bit of context, and I'll be here during the 2 days, so if anything that I say piques anybody's interest and you want to partner and collaborate on anything, please let me know. So I always like to start with a little bit of history. A lot of the research labs in the United States got underway in the middle of the last century. Of course, this was a time of turmoil. We were in the midst of World War II. This is a picture of one of the major developments from World War II. It's a picture of a V-2 rocket. The Germans launched thousands of these rockets, and these were, of course, weapons of destruction at the time. After the war, both the US and Russia got their hands on some of these V-2 rockets and began experimenting with them, and a curiosity set in on how we might be able to use these kinds of vehicles to expand scientific discovery and exploration in other dimensions. And so some of these launches were actually happening from White Sands, New Mexico, and some of APL's earliest scientists and engineers. APL was established in 1942, right around this time. Some of APL's first scientists and engineers were asked to serve on review boards and advisory committees for where these launches were happening. And one of the early ideas was to put a small 16-millimeter camera on one of these V-2 rockets as it was launching. And what I'm about to show you is the actual video of that launch. And so this rocket actually exceeded the von Karman line and flew into space. And this is the footage from that 16-millimeter camera. And you can see this beautiful panorama of the limb of planet Earth taken from this video. And so this is actually the first image of a planet that was ever taken from space, and it was taken by the Johns Hopkins University Applied Physics Lab. And so APL as an organization, wasn't necessarily set up for space exploration, but I like to say that space exploration has been in our DNA since our founding days, just a few years after the lab was established. We didn't miss a beat right after that. About a decade after that, there was a seminal moment where the Russians launched the first artificial Earth satellite, Sputnik, of course. This was a wake-up call to the country, wake-up call to the nation. And a lot of people started investigating, trying to understand what this satellite was doing, where this satellite was headed. APL scientists and engineers were a part of those investigations and were able to immediately track this spacecraft and be able to kind of predict where the spacecraft is going to be. In fact, initially they thought that there might be something broken or malfunctioning within the spacecraft because the frequencies were kind of oscillating in a strange way. But they were very quickly able to link this to the Doppler effect. And so you were basically seeing the spacecraft as it was coming overhead and as it was receding. But then they had the intuition to flip that problem around, right? So if you know exactly where the spacecraft is, you can actually use the spacecraft to tell you where you are, right? And that's a very important question because, for example, if you want to pinpoint the locations of our submarines and other vehicles across the ocean, that could be an important data point. And so APL immediately began kind of reverse engineering this problem, and within the same year began designing and building the first experimental satellite navigation system. We call this the transit system, and just a couple years later they had constellations of these spacecraft that were launched as a part of the transit system, and this basically became the precursor to modern day global positioning system, and is one of the 9 defining innovations of APL over our nearly 80-year history. So if we fast forward to today, APL is the largest university-affiliated research center in the country with 14 of these organizations across the U.S. These are strategic organizations linked with an academic institution, so we're one of the divisions of Johns Hopkins University, and we maintain and provide critical capabilities to support the U.S. government. We have a lot of different sponsors, a lot of different agencies within the Department of Defense that we work with across APL. I'm in charge of the civil space program, where almost all of the work that we do is in support of NASA, and even within NASA, it's really the Science Mission Directorate and the Space Technology Mission Directorate, like the LSIC consortium. This is a view of our campus right now. This is kind of a view from this building, almost from this building, looking north. So beautiful campus here. We also have some satellite campuses across the country. We have about 8,000 staff across the lab. We've had a significant amount of growth in the last few years. And our vision at the lab is to create defining innovations that ensure our nation's preeminence in the 21st century. It's a very important vision statement. We're fairly selective in the type of work that we take on at APL, and we try and matrix any new opportunity against this vision statement and decide what we want to pick up. There are several different ways to kind of characterize the organizational structure of APL. One of the sponsor-facing units of the lab are called mission areas, and so there are 12 mission areas at APL. So if you want to kind of get a sense of the kind of work that's happening at APL, you can just read the titles of these mission areas. Mission areas are responsible for executing all of the work that we bring in, also for winning new work and competing for and being directed new work where we can provide something that the government needs, managing internal investments and things of that source. The mission areas are also grouped into sectors. So I'm a part of the space exploration sector. Bobby Braun is the head of the space exploration sector. There are 2 mission areas in the sector, civil space and also national security space. And all of these mission areas get together frequently, roughly once a week, once every 2 weeks. We're all sitting together, sharing ideas, sharing technologies that might be developed elsewhere at the lab and seeing how they can influence our civil space program. So the framework that we have for developing space science missions, which is the biggest piece of our civil space program, is first off, it's a science-driven organization, but it's integrated within what's effectively a full NASA mission management framework. So that starts with research. So we have over 150 very active space scientists in the space exploration sector that are pushing scientific discovery, identifying the big challenges and the questions that we want to go after in our space exploration program. But then within the lab, we've got the capabilities to conceive, design, build, test, operate highly complex, think $1 billion plus large NASA space science missions, as well as instruments for those missions. Strategic partnerships are key to the success of this cycle, and so we partner with industry and other organizations, other NASA centers, academia throughout this process. And that reach back that we have to the rest of the lab really enables some unique opportunities for us. So if you look across several of our missions, Messenger planetary discovery mission that went to Mercury, or Parker Solar Probe, or the DART mission that we just launched, I'll say a little bit more about these through the presentation. But all of these leverage some piece of technology or some piece of capability that was developed elsewhere at the lab, and we were able to find a purpose for it to enable innovation for a NASA program. So let me hit on 2 themes today that are kind of the core pillars of our civil space program at APL. The first one is solar and space physics. So this refers to, heliophysics is another word for solar and space physics. This is a study of the sun and how the sun is influencing our solar system, impacting our planet, as well as our heliosphere. So first, the sun is the lifeblood of our solar system, right? The sun it's 99.8% of the mass of our solar system. Energy generation in the sun is equivalent to billions of hydrogen bombs going off every second for billions of years. And so the Earth and other planets in our solar system are really at the mercy of what the sun decides to do and what happens on the sun. And so this is a big focus of our program here. Here's a little animation that shows the flow of radiation and solar wind and energetic particles from the sun that's moving into all different dimensions of space. And fortunately, our planet has a magnetic field, and that magnetic field protects our planet from this harmful radiation. But occasionally the sun can have a coronal mass ejection or a solar flare where you get millions of tons of plasma shooting out at a high speed that impacts our planet, and it can overwhelm this magnetic field. We've had several cases of that. In fact, just recently, I think everybody probably knows there were 40 SpaceX Starlink satellites that didn't reach their orbit because of some thermospheric expansion that resulted from a space weather event. So we're very interested in studying this phenomenon and finding ways to predict it and forecast it, right? To bring space weather forecasting up to the kind of level that terrestrial weather forecasting has evolved to over the last decades. And so this is a big part of our program here. And so I want to point out two new developments at APL. So one is NASA asked us to develop a gap analysis for space weather, that is, identify those assets that we have in space right now that are either reaching the end of their life or new assets that we need within the Sun-Earth system to be able to better predict and forecast space weather. And so we recently developed a gap analysis. You can find it online that advocates for the kind of technologies, the kind of measurements that we need. And this will be considered by the Solar and Space Physics Decadal Survey, which is underway right now. And the second is a recent win of a DRIVE initiative, really a center of excellence called the Center for Geospace Storms, where we're trying to develop the kind of the state-of-the-art model for being able to predict this space weather phenomenon. We were just awarded this project a couple of months ago, and it's a multi-year, it's a 5-year project. Very, very strong, broad partnerships across the community for this. We also love to build spacecraft that can study the sun and study the sun from different vantage points. This is a view of a spacecraft that we built and launched in August 2018 for NASA called Parker Solar Probe. This is a $1 billion mission. It's been something that the science community has been calling for more than a half century, but we really lack the technology and the innovation to be able to build a spacecraft that could literally fly through the outer atmosphere of the sun. So just to put this in perspective, right, typically for space weather research and research in heliophysics, we're looking at the sun from 93 million miles away, right? And Parker Solar Probe is designed to fly within 3.8 million miles of the sun's surface. And the sun is 1 million miles across, so flying 3.8 million miles from the sun is pretty incredible. And it's a marvel of engineering. That thermal shield that you see right there, that's a 8-foot carbon composite shield that can reach temperatures of 2,500 degrees while protecting the spacecraft and keeping all of the instruments and electronics at room temperature. So this spacecraft has been very successful. We launched it in August 2018. Right now it's orbiting just shy of 5.5 million miles from the sun's surface. Over the next couple of years, it's going to dive in even closer to the sun and eventually end up at 3.8 million miles. There have been more than 600 research papers published from Parker Solar Probe data, and really new insights on understanding solar phenomenon with an in situ investigation at the source of that phenomenon as opposed to 93 million miles away. Following Parker Solar Probe, we have another heliophysics mission that we're building right now at APL called the Interstellar Mapping and Acceleration Probe. This is a partnership with Princeton University. The PI is from Princeton University, as well as many other organizations that are contributing, providing instruments and other subsystems to the mission. IMAP is a great follow-on from Parker Solar Probe. It's a mission that's going to orbit at the first Lagrange point at L1. And it's a mission that's designed to study the solar wind that comes from the sun, passes past Earth, and travels all the way out to the outskirts of the heliosphere. And through the spinning spacecraft, we're able to essentially build a very high-resolution map of the outer heliosphere of our solar system. And that's a boundary that really represents a kind of a protection that our solar system has from the rest of the Milky Way galaxy. And there's a lot of uncertainty on what the shape of that heliosphere looks like. But we can also do this with IMAP as a system level experiment. We have 10 different instruments on IMAP. And so within the same mission, we're able to study energetic particles and ions and dust over a very broad energy range. So this is a mission that's being built at APL right now and will be launching in February of 2025. We have our critical design review coming up later this year for this mission. Very quickly, a new mission that we have is called EASY, the Electrojet Zeeman Imaging Explorer. This is a small mission, a very innovative mission that is a strong partnership with industry as well as with JPL, where we're flying 3 CubeSats and on a kind of a pearls of string configuration. And these 3 spacecraft are going to study both temporal behavior and dynamical behavior in the upper atmosphere of the Earth, where we see very energetic processes driven by the interaction of solar radiation and our atmosphere. This is a mission for which we have a preliminary design review coming up later this month, in fact. And then finally, one of the things that we enjoy doing for NASA is formulating new concepts. And so NASA has actually asked us to study a mission concept that also the community has been asking for a long time, as an input to the Solar and Space Physics Decadal Survey that's getting underway. And we call this mission Interstellar Probe, which is a fascinating, inspirational mission to take humanity's first intentional steps into interstellar space with a modern set of instruments and fly through this heliospheric region and study it in detail. And we've just completed our study for Interstellar Probe and delivered that to NASA, and it'll be evaluated as a part of the Decadal Survey. And the goal here is really to do cross-disciplinary science, astrophysics science, planetary science, and heliophysics science, travel out to 500 astronomical units, do exciting science on the way to getting into interstellar space, and also when we get to that vantage point, and through multiple generations. This is a spacecraft that's meant to survive for, say, 50 years and serve the interests of multiple science generations. The other big pillar of our civil space program at APL is planetary science. Planetary science is the largest piece of NASA's Science Mission Directorate. It's a very, very important and strategic part of our portfolio as well. Let me start with our most recent launch, DART. So DART is the Double Asteroid Redirection Test. This is NASA's first planetary defense program. Planetary defense is a new program line that stood up at NASA to achieve several goals. One is to find all near-Earth asteroids and just catalog them. Two is to learn about them and figure out what their characteristics are, what their sizes are, what their compositions are, what their orbits are. So if one of them were to impact Earth, we would be able to anticipate what the damage could be. And then third is to do something about it, right? So if we had an asteroid that was hurtling towards planet Earth, have a technology that's ready to be able to mitigate an asteroid strike of Earth and potentially save the planet and certainly save life. And we're bombarded by asteroids all the time, and so this is an important technology. So we came up with a concept called DART, the Double Asteroid Redirection Test, that's targeting an asteroid that does not pose a threat to Earth. It's an asteroid that's orbiting the sun. It's actually a binary asteroid system. We've got a large asteroid and a small asteroid. The small one's about 150 meters across. DART is a spacecraft that right now is traveling at almost 14,000 miles an hour. It's going to hit that small asteroid, and on September 26th of this year, for the first time, humanity is going to move a rock in space. So this is really, really exciting. It's a scalable experiment. We've got other technologies we want to study that have been advocated for through the Decadal Survey, but DART is a great example of an innovative, low-cost planetary exploration program. Let me show you a little trailer of DART. Okay, there you go. So DART's on its way. We're only a few months away from impact on September 26th. You saw in that video, by the way, there's a number of new technologies on the DART spacecraft that we haven't flown before, such as the rollout solar arrays that you saw, as well as some other things. And the terminal impact is very exciting for DART. It's again one of these examples where we leverage technologies that were developed by the Air and Missile Defense Sector at APL to autonomously course correct the spacecraft as it approaches its target. DART will actually only see the smaller of the two asteroids, the one that it's intended to target, just a little bit before impact, and the spacecraft will autonomously go in there. We're not joysticking it or anything. It'll find the small object, find the centroid, hit that small object. So really innovative, exciting mission. And so you'll be hearing a lot more about that over the coming months. Finally, I'll close by talking about, I think, what I believe to be one of the most exciting areas of all of space science, and that's the study of habitability in the universe and the search for life in the universe. If you go back a few decades, right, you look at a beautiful picture of planet Earth and you see its distinctive ocean, and for a long time we thought that the Earth was unique because it had an ocean. It turns out that that's not the case. The Earth has a surface ocean, but there are many objects in the solar system that have oceans. It's just they happen to be subsurface oceans. More recently, we've even seen evidence from Hubble Space Telescope observations and Cassini observations of these oceans venting through fissures that are created on the surface of these because of the tidal pulls of the large planets that the moons orbit. And so here are a few examples. So Europa, that's one of the nearest ocean worlds to us. It's a moon that orbits Jupiter. It has twice the volume of water as Earth. Titan, which is the largest moon that orbits Saturn, has 14 times Earth's volume. And Enceladus, which is a very small moon that orbits Saturn, where Cassini saw evidence of this water spewing into space. So we're involved through a number of partnerships in a number of different missions that are destined to explore these ocean worlds. And it's really a part of an astrobiology campaign that goes from understanding habitability, whether or not these worlds could be habitable, understanding the chemistry on these worlds prior to the biology set in. So if you look at a world like Titan, we actually believe it to be kind of an early analog of Earth before the biology set in. So you can kind of go back in time and see what this world was like. And then actually doing the astrobiology, right? Let's actually tasting some of this material that's coming out of these oceans and figuring out whether or not there is life on these worlds. So the first one is Europa Clipper. This is a very large mission. It's one of the largest programs at NASA, a strategic partnership between the Jet Propulsion Lab, which is the lead, and the Applied Physics Lab, APL, which is a partner on this mission. APL's contributions to Europa Clipper include developing the propulsion module, developing the RF communications system, and also being in charge of the solar array development. And we're also developing 3 instruments for Europa Clipper, including the primary imaging camera. We call it the Europa Imaging System. It's actually two instruments in one, the wide-angle camera and the narrow-angle camera. And so all of this work has been developed. All of this has been one of our largest programs in civil space over the last 5 years. We're actually at the tail end of that development. In less than a week, we're going to be shipping the propulsion system and the RF module to our colleagues at JPL. And in about a month, a little more than a month, we're going to be delivering 2 of the science instruments. We've already shipped one to Europa Clipper, and then everything gets integrated on the spacecraft, and late in 2024, Europa Clipper will launch. Dragonfly is the second mission there. I'll speak about that just in a second. I've got a little video on it. The third one I'll forward to, Enceladus Orbilander. This is a concept, so this is not an approved mission yet, but this is a concept that we formulated here at APL in the last 2 years to develop a spacecraft that would not only orbit around Saturn's moon Enceladus, where we see this water spewing into space, but it would also land. So we call it Orbilander because it orbits and lands. And then when it lands, it does a very high signal-to-noise astrobiology experiment sampling that water. And so this is a mission that we submitted to the Decadal Survey and was very highly ranked by the Decadal Survey. So hopefully in the coming decade, 2 decades, this is a mission that we can fly at NASA. Just on Dragonfly, let me show you this beautiful video of a view of Dragonfly. So this is a nuclear-powered dual quadcopter. It's about the size of your car. It's about 11 feet across. And we'll spin up the rotors right as we enter the thick atmosphere of Titan. So Titan's an exotic world, not only because it has an atmosphere that's thicker than Earth, but it also has a lower surface gravity. So if you combine those 2 things, it's a perfect place to fly. Dragonfly is loaded with scientific instruments. So the spacecraft will come in, or the rotorcraft will come in. It'll land on a safe place autonomously. And then we've got a drill, so we can drill into Titan soil and sample that soil. We have a mass spectrometer. We have seismometers. We've got a weather station on board. We've got imaging cameras. We also have a gamma-ray neutron spectrometer to do compositional analysis on the surface. Once we're done with a given location, we'll spin up the rotors, the spacecraft will fly to its next destination, and over the course of about 3 years, we'll traverse a couple hundred kilometers on Titan and explore the geological diversity and the prebiotic chemistry of this really, really exotic world. So Dragonfly is a mission that was selected a couple years ago. We're in the design phase of it right now. We have our preliminary design review coming up later this year, and our plan is to launch this mission in the summer of 2027. It'll take about 6 or 7 years to get to Titan, and then we start our scientific exploration in 2033 for a period of 3 years. So very, I think one of the most exciting NASA science missions that's ever been competitively selected, and we're really, really proud and happy to be leading this project. That was a very quick snapshot of some of the work that we do in civil space here at APL. We have a beautiful new website that I encourage people to visit, civspace.jhu.apl.edu. You can see a lot of our innovation in our technology and our engineering and our science, as well as some of the instruments and some of the other missions that we're developing. Okay, I will stop with that. Thank you, everyone. So with that, I'd like to introduce Dr. Bobby Braun. Bobby's my boss. He's the head of the space exploration sector at APL. He joined us just recently and has dove right in, and has been a pleasure to work with him and learn from him. And Bobby's going to introduce our next keynote speaker.
Thank you, Jason. It's great to be here with you all today. I'm excited to learn about some of space technology's most critical contributions to NASA's Artemis program and to getting back to the moon. What you all are doing here is fantastic, and appreciate you all being here and the work that's going on. Thank you, Jim, for all that.